When you interact with an AI today, whether it's a chatbot writing an email, an image generator creating art, or a code assistant debugging your software, it feels like pure magic. It's a digital intelligence, seemingly pure software, living in the cloud, responding instantly to your every command, conjuring solutions out of thin air. You type a prompt, and within seconds, a coherent email appears, a stunning image is rendered, or complex code is debugged. This seamless, almost ethereal experience has redefined our perception of technology. But underneath this elegant, almost invisible software facade lies a brutal, physical reality, a massive, power-hungry infrastructure of specialized hardware. This isn't just clever code. It's tons of metal, silicon, and electricity humming away in vast, purpose-built facilities. The hidden tension in modern AI is that what appears to be a sophisticated software product is, at its core, a hardware business. Specifically, a GPU business. Let's demystify this. When you use an AI, you're interacting with a trained model. This model is a complex mathematical representation, a vast network of interconnected nodes designed to recognize patterns and make predictions. Think of it like a highly specialized, digital brain, honed through immense exposure to data. To create and run these intricate models, traditional central processing units, or CPUs, designed for sequential tasks, simply aren't efficient enough. A CPU is like a single, brilliant chef, capable of preparing any dish, but only one at a time, meticulously following each step. This sequential nature is perfect for general computing tasks, but utterly inadequate for the sheer volume of repetitive calculations required by AI. Enter the graphics processing unit, or GPU. Originally developed for rendering complex video game graphics, pushing millions of pixels to your screen simultaneously, GPUs excel at parallel processing. Instead of one brilliant chef, imagine 1,000 line cooks, each performing a simple, repetitive task, but all at the same time. This allows for thousands, even millions, of calculations to happen simultaneously. This parallel processing capability makes GPUs uniquely suited for the matrix multiplications and tensor operations that underpin neural networks. These are the fundamental mathematical operations that allow AI models to learn from data and make predictions. Whether it's the arduous process of training a model from scratch or the rapid execution of inference to generate a response, GPUs are the engine. The life cycle of an AI product begins with training. This is where the model learns from vast datasets, petabytes of text, images, audio, and code, adjusting its internal parameters over countless iterations. A state-of-the-art AI model today can have hundreds of billions, even trillions, of parameters, each needing fine-tuning. Training a foundational model like GPT-3 or Llama 2 can require thousands of top-tier GPUs running continuously for weeks or even months. This consumes immense amounts of power, often equivalent to that of a small town, and generates significant heat, necessitating massive, complex cooling systems. This isn't happening in your garage. It's happening in massive, purpose-built data centers, sprawling across acres, primarily owned and operated by hyperscale cloud providers like Amazon Web Services, Microsoft Azure, and Google Cloud. These cloud providers rent out access to their vast GPU clusters. This is where the concept of cloud costs becomes paramount. For a startup or even a large enterprise, the upfront capital expenditure to build such a cluster is prohibitive, making cloud rental the only viable option. Every minute a GPU is running, it's costing money. To put this into perspective, a single high-end AI GPU like NVIDIA's H100 can cost $3 to $5 per hour to rent in the cloud. Multiply that by thousands of GPUs, running 24/7 for months, and the costs quickly skyrocket. Training a large foundational model can easily run into the tens or even hundreds of millions of dollars in compute costs alone. It's like renting a supercomputer by the minute. Once trained, the model needs to perform inference, making predictions or generating content based on new inputs. While less computationally intensive than training, inference still demands GPUs to deliver real-time results. When you ask ChatGPT a question or Midjourney generates an image, that's inference in action. Speed is critical for user experience. If an AI takes seconds to respond, users quickly lose interest. GPUs provide the necessary parallel processing power to handle billions of inference requests daily across millions of users, ensuring that instant, magical response we've come to expect. Most AI products you use today don't run on your local device. Instead, your request is sent across the internet to a server farm where GPUs process it, and the result is sent back to you. This entire journey, from your phone to the data center and back, often takes milliseconds. This interaction is often facilitated via application programming interfaces, or APIs, which allow different software systems to communicate seamlessly. Think of an API as a highly efficient waiter taking your order, your prompt, to the kitchen, the GPU cluster, and bringing back your meal, the AI's response. It's the invisible bridge connecting your device to the powerful hardware. The pricing models for AI services, whether it's a monthly subscription, a per token charge for text, or a per query fee for images, are directly tied to this underlying GPU usage. Every word generated, every image created, every line of code debugged consumes a fraction of a GPU's processing power. High usage for the end user translates directly to higher operational costs for the AI service provider. This brings us to the crucial element of the supply chain. NVIDIA, with its proprietary CUDA platform and specialized hardware like the H100 and A100 GPUs, holds a near monopoly on the high-end AI GPU market. Their technology is the de facto standard, making them the gatekeepers of advanced AI compute. CUDA isn't just hardware. It's a comprehensive software ecosystem that developers use to program GPUs. This creates a powerful moat for NVIDIA, as switching to alternative hardware from competitors like AMD or Intel often means rewriting significant portions of code, a costly and time-consuming endeavor. This lock-in solidifies NVIDIA's dominant position. This hardware dependency creates significant economic implications. For startups, the barrier to entry for training a foundational model is astronomical, often requiring hundreds of millions, if not billions, of dollars in compute alone. This isn't just about buying chips. It's about the power, cooling, and specialized engineering to run them. Cloud costs for AI are not trivial. They can quickly become the single largest operational expense for an AI company, dwarfing software development salaries, marketing budgets, and impacting profitability. If these costs are too high, it can force AI companies to raise their prices, sometimes even leading to user churn if the service becomes unaffordable or less competitive. This dynamic gives a massive advantage to big tech companies with deep pockets and existing cloud infrastructure. They can afford to buy or build their own vast GPU clusters, securing their compute supply, negotiating better deals directly with NVIDIA, and even designing their own custom AI chips, like Google's TPUs or Amazon's Inferentia. The take rate of cloud providers and NVIDIA is immense. They are the picks and shovels sellers in this AI gold rush, capturing immense value at the fundamental infrastructure layer. While everyone else is digging for gold, NVIDIA and the cloud giants are selling the tools and charging for the land, consistently profiting regardless of who strikes it rich. Understanding this helps explain why AI product pricing can sometimes feel high. You're not just paying for clever software. You're paying for a slice of incredibly expensive, power-hungry hardware, maintained and operated 24/7 in a secure, climate-controlled environment. It's the cost of raw computational power. The future will undoubtedly see more efficient models, custom silicon from various players, and perhaps new architectural innovations. We're already seeing efforts to make models smaller and more optimized, and companies like Apple are integrating neural engines directly into their devices for edge AI processing, reducing reliance on the cloud. However, the fundamental need for parallel processing hardware, whether it's a GPU or a specialized AI accelerator, remains central. The form factor might change, the efficiency will improve, but the underlying requirement for massive parallel compute power will persist as AI models continue to grow in complexity and capability. So, the next time you marvel at an AI's capabilities, remember the silent, humming server racks, the vast power lines, and the specialized chips working tirelessly beneath the surface. Modern AI products aren't just clever algorithms. They are sophisticated software layers built on top of a capital-intensive, physical GPU infrastructure. The true magic isn't just in the code, but but in the powerful hardware that brings it to life, transforming electricity and silicon into intelligence.